the logos there a bit, and we'll decrease the ones that say going on is we're going to start with and initially we're going to assume we don't know, okay, so all the logos are zero, exactly. So we're going to start with a matrix of zeros, perfect. And then we're going to receive a LiDAR scan. So if our orbit is here, our LiDAR scan will actually look something like this. So we'll have a bunch of rays that go through the map and end at some endpoints here, okay? So now what should we do? So we know that at these endpoints here, these green ones, that's where we hit. So there's an obstacle there. So we should increase the logos. How much should we increase them? We said, well, we're going to use a very simple model. We said something like log of true positive versus false positive. How often does our sensor make a mistake? We said for the LiDAR, it's a very accurate sensor, so one idea is to say 90% is correct. So I would add, so it's essentially plus minus log of 9. So if the LiDAR says something is occupied, add log of 9. If the LiDAR says something is free, subtract log of 9. So for the green ones, right, after, let's say this is my first LiDAR scan, I started at 0. So these ones should become log of 9, log of 9, log of 9, and log of 9. Okay, 9 was something like 90%, right? If you want 80, you can do 4 over 80 over 20, it's log of 4. So that value you can tune, it doesn't matter. I would say log of 9 is fine. Okay, we increase the logos for these, but the LiDAR tells us a little more. It told us that those are occupied, but the ones along the ray are free. So we should subtract or reduce the logos of all of these. So this one, 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 this one. These should now become minus log of 9. Does that make sense? Because the LiDAR says, okay, my ray managed to pass through here without hitting, so this is very likely free. So that's it for the mapping. So over time, like at the second time step, again, you find which cells the LiDAR passes through. The ones that pass through, subtract log 9. The ones that you hit, add log 9. So now the main question is, yeah, go for it.
So when you're calculating whether the ray goes through there, do we use the ray trace function from the DT
Oh, no, there's a, yeah, so you're right, we need to find, how do we find which cell do we pass through? And there's a function in the utilities called Brestingham. So Brestingham essentially takes the start point and the end point and tells you which cells you go through.
Okay.
Actually, it doesn't need the map because it already assumes you're already in cell coordinates. So it's just taking a line and it's telling you which, it doesn't need to know the map. It only needs to know start and end, and it's going to tell you, okay, this line passes through these 5 cells. That's what Bressingham does. It doesn't know whether it's occupied or free, it doesn't need to know the map. It just needs the start and the end, and tells you the cells in between. Yeah. Other questions?
I guess the last thing, when we're trying to pass the image onto the floor, and we basically say, hey, is it close enough to 0? Then do we want to like cast that texture onto our free space in the same map? Do we want to like basically make those cells the sum of the colors that like our RGB the image shows that location?
Yes, exactly right. So when you take your pixels from the camera frame and you're using the depth to convert them to the world frame, they will have different heights in the world frame. So ones that have a height of 1 meter or 2 meters are way above ground, so we're not going to care about these. Find ones that are close to 0 height. Because there's some error, I would go anything that has a height of minus 0.1 plus 0.1, I'm going to consider ground. So this is based on, in the world frame, the height is the z-axis. So for z between plus minus 0.1, I'm going to consider those. So that take their x, y coordinates, they will tell me which cell I'm floating in. And I'll create a second map so that you don't mess up your first one. Just make a second map which is the same size. So you have another occupancy grid, well not really occupancy grid now, but for each cell add 3 dimensions here, I guess. So that means something like numpy dot array,
It's very messy, but like you can see relative colors.
zeros. Sorry,
And I just assume that's
you can initialize this as numpy zeros. However large your map is, let's say 100 by 3. So that will give you space for R, G, and B. So from the XY coordinates, you find which cell you fall in, and you save the RGB value there. If several points fall in the same cell, which will happen, you can just take the latest RGB. You don't have to average or do some smoothing or just take whatever the latest value is good enough. Yeah. You can ask more questions. It's okay. I'm sure others have similar questions. So.
Yes.
I suppose the last question I had to ask is like when we're employing GTSAM at the end, we basically just like we start out using all these kind of functions that we built, or like Russian. Do we just do the whole thing in GTSAM as the last step? Is that like and use the packets?
No, the mapping will always be this. The mapping GTSUM only helps us with the trajectory estimation. So I would say that the bare bones completion of the project goes like without even using GTSUM. The simplest or the fastest way to getting a first version of the project is use the IMU and the linear velocity to predict your motion. Then do the mapping and the texture mapping, and that's it. So you have the trajectory, you have the occupancy grid, you have the map, you're done. If you want to improve on this in any way beyond, you can consider using ICP to match the LiDAR scans. So in theory, that should improve a little bit on the motion model. In practice, what I've seen is actually not true, actually seems to hurt things a bit, but that's okay, you can try it. And then if you want to improve even further, that's when you would consider GTSUM. So GTSUM will only help with the trajectory, it doesn't change the map, or you wouldn't implement the map in there. So GTSUM will take your estimates of where the robot goes over time, as well as constraints on the relative pose, which you can get from ICP or from your encoders and IMU, and impose these as constraints. What GTSUM does is optimization over your whole trajectory to try to get a slightly better trajectory. Yes, so I would say minimum deliverables would be encoders, IMU, trajectory plus mapping. If you have more time, the second, I guess, major deliverable would be ICP, warm up and trying it on the trajectory. If you still have time, I would try GTSUM, just learn how to use the library, play with it a bit, because it's one of the most widely used libraries for mapping. Yeah, for some, sorry.
And one last thing, when we're plotting the trajectory, like we take the trajectory we plot in part 1, would you just say, hey, plot that on your occupancy map as I've been there now, I know that it's open, or
Yeah, you can plot it on top of the.
but you don't have to necessarily, but
You can have two separate plots, one of the trajectory, one of the map, or you can plot them on top of each other. I think on top of each other looks nicer because it shows you where you've gone.
Yeah.
But you don't have to, even if you have them separate, that's good.
Okay, cool.
Oh,
Yeah. Okay, let's go with your question.
For the last part that we should find some loop closure. There is 2 algorithms. The first one is like the frames that are like 10 frames apart. They find some loop closure. For the second one is that we should compute, for example, frames that have similar poses, right?
Yes.
And should be like in the class, I think with the metric was the norm of the log of first pose inverse times the second. This is the metric that we should compute for each pair of. Like,
Yeah, good question. I think this part is fairly open-ended because we didn't discuss how to do it in class, so you can play with it or try different things if you have time. Maybe even simpler is to only look at the translation, not the orientation, because even if one frame looks this way and another frame looks this way, according to the log t inverse times t metric, they might not be so similar, but they still have some overlap in the field of view. Like looking this way, we might see a little bit of common, and looking this way, we might see a little bit of common. So you might actually be able to do a loop closure just based on this. So your metric can be just based on position distance, not necessarily pose distance. I think pose distance is reasonable too. Yeah, I think with pose distance, you're going to have fewer candidates for loop closures, but they will be higher quality in that you have poses that are quite aligned.
But I think that the pose like frames that are near each other should be very similar, right? For example, the first frame and for example the fourth frame should have really similar poses.
True, but yes, but really the loop closures you're most interested in, or the ones that will have the largest impact on your performance, are this one and this one, for example, or this one and this one. So ones that you get when you're actually coming back. So they're not so close in position and orientation, but they are seeing assuming they can see the same part of the environment. So let's say this one sees this, and let's say this one sees this, right? So this space here is common between the two poles. So both poses are observing the same part of the environment or the map. So somehow there's a transformation between them which can align them. So if you can kind of associate a pose in the beginning of your trajectory with a pose in the end of your trajectory, this actually creates a constraint for the whole loop. So that's why it's called a loop closure. This will have a big impact on everything. If your constraints are only like from here to here and here to here, it will have a smaller impact on the overall accuracy.
So you suggest that instead of just looking at the poses, we better like to weight it a little smaller and then try to define poses that are like in the frame or at the time six they are far apart, but they might be similar.
Yes, exactly. Ideally we want something that are far away in time steps, and second, really the best would be do their fields of view overlap. So you don't have to do this for the project. If you have enough time and you want to try it, you can think of doing some sort of intersection between, so your field of view is some sort of a cone or part of a circle thing. So you can take the field of view for this pose and field of view for this pose and do intersection. So if those two sets intersect, these are loop closure candidates.
Okay, so if I want to like double check that, for example, my idea is good, the most perfect curve that we can get is that the end and the start they're aligned, right?
So I think this robot was driven by a joystick by a human. So I don't think the human ended exactly at the same point where they started. So I would say maybe not. I think the motion model, what you get from the odometry and the IMU is actually quite close already. I think you can improve on this a little bit. I think the end poses are a little bit closer, but they're not exactly on top of each other because it was someone just walking around. They end up in the same room, but maybe not exactly where they started. Yeah. Let's go with you.
Like building on to that question, actually using GTSAM as a library seems pretty straightforward, but I'm failing to understand the actual concept behind loop closure. Like, could you explain loop closure basically?
Yeah, I mean, look, so yes, I will try. Let's see. Yeah, okay. So when we are using the motion model and the IMU, the linear velocity from the encoders and the angular velocity from the IMU, you can imagine if these circles are poses, we're introducing constraints like this. So for every consecutive pose, the IMU and the encoders tell me how much they move and how do they rotate. So over time, my trajectory estimate is kind of based on this. And the problem with this is that if I have some small error here, the transition from here to here is not bad, it's accurate because it's small error. But if I have a small error here as well, the transition from here to here is not bad, it's accurate. But now the transition from here to here has two errors accumulated. And as your trajectory gets longer and longer, these errors accumulate. So over time, the true trajectory and your estimated trajectories will be quite far from each other because the tiny error, even if you have the most accurate sensor, accumulates over time. Okay, so the idea of loop closure is to try to correct this. And how can I correct this? By introducing constraints that are not between consecutive poses, we might actually be able to correct it. Okay, so the simplest idea of loop closure is to start creating constraints like this. So now we're going to have these little loops, which are two constraints from the motion model. And let's say this orange one is by matching the scans of what? The first pose, so let's say there's some wall here, some object here. So the first pose here, let's say, has a LiDAR scanner. So we're going to receive a LiDAR scan, something like this. And then let's say your third pose here also has a LiDAR scanner, so it's going to receive some, let's say, scan like this. So if you match the green scan and the magenta scan with ICP, this can tell you what's the relative transformation between this pose and this pose, and essentially create this orange constraint. And you can do this again for every 2 consecutive poses, for example. So you have orange constraints, between any 2. Okay, so now this is a lot more constraint, so you're making sure that kind of the motion model agrees with the scan matching, and this can improve things further. So you can add these sort of constraints between 2 or 5 or 10 consecutive poses, and as I said, finally you can also, some of the best ones to consider are ones if you end up coming to a place you've been to before, if you can somehow introduce a constraint between some poles here and some poles here, that like they're much different time in the future but similar place. This will now create a constraint for your whole trajectory, so it can have a huge impact on this accumulated error.
Thanks.
Yes?
We said that we could still do this loop closure even if we didn't get ICP scan matching working.
Yeah.
And I guess I'm wondering if you could talk about, like, intuitively for me, I think that we wouldn't be adding anything different because if our relative pose is just defined by the odometry, which is already the trajectory, then
Yeah, then there's
like
nothing to
what do we
optimize.
do with the loop closures if we don't have the ICP scan matching working?
I don't know. I guess I still wanted you to try the GT-SAM, but the minimum what you can try if the ICP does not work is to use the motion model and just add the constraints. But yes, you're right. If you run optimize, it's not going to optimize anything.
Okay.
So your output will be the same, but at least you will have used the library, which I think is a good step. But yeah, to add some meaningful ones, you would want to get ICP working. I'll come back to this because I wanted to ask you if you managed to get ICP working. Okay, no? Okay, we can discuss this more. Let's cover it.
Okay, so I was looking at the occupancy grid mapping stuff last night. I think I understand what Bressenham 2D does. The map correlation function though, I don't know what that is for. And then how do you, we don't need, okay.
Yeah,
Okay.
I left that because it shows an example of how to create a map
Mhm.
in the test map correlation.
Okay.
And because in the lecture we mentioned that if you want to do a particle filter, you can compute correlation. But yeah, you don't have to look at that part.
Okay, and then show LiDAR. Do we need that one either? No, okay.
Just a visualization,
Okay, gotcha. So
just so you can know what the LiDAR data is.
I think you wrote it earlier, like we're creating this grid and it's just a NumPy array of zeros, like 100 by 100. And then we're using like the LiDAR data to populate that array. Okay,
Exactly.
Gotcha.
Yeah. So when you take your LiDAR scans, you convert from LiDAR frame to body frame to world frame.
okay,
Then you have the start point is the road's position, the end point is the world frame coordinates of each point.
Yeah.
You call Bressingham with this start and end. This will tell you which cells the LiDAR passed through.
Mm.
The cells along the array, you subtract log of 9. The last cell where the LiDAR hit, you add log of 9, and that's it. That's the log odds. So you update your zero matrix of zeros with these plus minus log odds at every LiDAR scan.
Okay.
That should give you the log odds.
okay, gotcha. And then converting LiDAR to world frame. I think I saw it on Piazza. It's like we just take the readings and then convert them to homogeneous coordinates or Cartesian.
Yes, so your readings are distance and angle.
Yeah.
So those are polar coordinates. So you need to go polar to Cartesian first, so you can get x and y.
Mhm.
Your z is 0 because your LiDAR is 2-dimensional.
Yeah.
So you have x, y, 0. And then you can start rotating and translating with LiDAR frame to body frame is just minus on the z-axis or something like that.
Okay.
And then body frame to world frame is whatever your odometry says.
Mhm.
So that will give you the LiDAR scan in the world frame.
Okay. And then one last question is the LiDAR angles. We weren't given an array of angles. We were just given like the increment and then the max and min. So we should create an array of angles that correspond to the ranges.
Yes.
But also like we're going from a negative value to a positive value. So like, should we split it at the middle and all the stuff on the right? We shouldn't do
No,
that.
you just have one array of the angles. So
Okay,
you
it's-
have the distances and the angles.
Uh-huh.
Positive or negative doesn't matter. These are the polar coordinates. So if you go polar to Cartesian, this gives you the xy.
Okay. Okay, gotcha. Yeah.
Okay, let's
Makes
take a
sense.
question on
Thank
this
you.
side. Maybe you can go first.
So theoretically, if you choose, if you define loop closure based on proximity, the criteria would actually be the logos and the two poses are looking at the same thing rather than actually the two poses of it.
Yes, exactly. Yeah, it's much better to think of, the two poses are looking at the same thing. Exactly. Yeah, that's what I was saying. You can think about your field of view is some set, some region, like a half circle or slightly larger than a half circle. For the two poses, you can think of intersections between those. Those are kind of, if their fields of view intersect, those are kind of loop closure.
One thing, basically, actually nothing. I don't get how you get the start and end point of the array.
Oh, the start point is always the robot's current position,
Oh, so
or the LiDAR's current position.
I can get that just from the motion model, right?
Correct, yeah. Yeah.
And the-
So that's the start. And the end point is from the LiDAR reading. From the LiDAR measurement, you have distance, right?
And that's in the LiDAR frame, so I get, I can work from the LiDAR to the body and then from body
To world. Yes, exactly. So the endpoints will be the endpoint and the LiDAR position is the start. Exactly.
So the 100 by 100 by 3 is just for one scan, right? And I make a new one for the next.
No, you would keep only a single map. I actually don't know if it's 100 by 100. I forgot what. You can play with how large the map is. What size are people using?
For the mapping, I'm using like a negative 30 by 30 on both axes.
Okay, this is in meters.
Oh yeah, in
And then what's
meters.
your resolution?
Oh,
0.1 or 0.25?
yeah, 0.1.
Yeah, 0.1. So you have how many? 600 by 600, something like that.
Yeah.
Okay, so your map is 600 by 600. That's fixed. You don't create a new one. You're just going to be updating it. So you have two of those maps. One is 600 by 600 by 1, and the other one is 600 by 600 by 3. So the one that's by 1, that's where you update the log odds. So places that the LiDAR passes through, you subtract log 9. Places that it hits, you add log 9. The other one that's 600 to 600 by 3, you take the RGB values from the camera, convert those to the world frame, keep only the ones that are close to the floor, so they have a height of plus minus 0.1, for example, and store their RGB value in the 600 by 600 by 3 map. They accumulate over time in the same map.
So do I from the camera, do I just overlay everything or only on the positive and log ones?
Oh, I see. You can just overlay everything. It happens that the camera only sees free space, so or on the boundaries of occupied, so you don't have to worry about logos. Your RGB values will end up corresponding to places with negative logos, but you don't have to explicitly check. It will be just a property of the camera. It cannot see through the obstacles. Yes.
So can you explain a little bit about what the noise model in GTSAM does? Just because in the lecture, you it did not explicitly mention.
Yeah, and we didn't discuss it. So even our ICP formulation is not probabilistic. So the noise model is the following. For example, from ICP you get a position and rotation, but ideally you want to get some uncertainty on that, like how accurate is your estimate. So for example, if you can imagine if each LiDAR has an error on the position of the point, so you can imagine along the rays there's some little Gaussian distribution which tells you exactly where the point is, then you can think of something like a probabilistic ICP formulation, which will give you not only the rotation and the translation, but some distribution over R and P. You can use that as the noise model in GTSAM, so this would take uncertainty into account. In our class, we didn't get so deep into estimating uncertainty of the scan matching and so on, so you can just put some value by hand. You can say, I expect ICP to approximate my relative pose relatively well, so it will be some diagonal 3 by 3 matrix where you have sigma x, sigma y, and sigma theta are sort of standard deviations of how accurate I think my relative pulse is estimated. So I would just tune those by hand, but in practice you would want to do it based on the noise and reservation model. Yeah, but for our project, just I don't know, use 0.1, 0.1, 0.01 and see how well that works.
And say if you introduce a loop closure between P0 and P10, so the restraint between these nodes should just be the relative pulse find by ICP between the cloud line of.
Yes, cloud 1 and cloud 10, exactly. Yes, yes. And ideally, those clouds should be on the same part of the environment so that we're registering something. If pulse 0 is looking this way, if pulse 10 is looking this way, if you run ICP, it will find some alignment between them, but it might be meaningless. Yeah.
So follow-up is our question. So, is it a good heuristic to use the ICP's error to sort of estimate the variance of the constraint?
Yeah, it's a good idea. I don't know how related they are, but yeah, you could. I mean, you can say it's proportional in some way. It's reasonable. Yeah, but I don't think you need to do much for the variance. Even if you keep it constant, it's fine. But it's a good idea to use the. Yeah, we can discuss more carefully what the variance should be, but it's more complicated. If you're curious and you want to read, I would suggest checking a paper called. Yeah, you can check something called CSM, which stands for Canonical Scan Matcher. The paper in 2006 or 7. I think this discusses how to get covariance as well for scan matching. And I think there's an implementation in ROS that essentially does the scan matching. So after our class, when you have time, if you're still curious, you can try this with some LiDAR data. So it's essentially doing ICP with some bells and whistles. There's some features, some covariance estimation, and so on. Okay, more questions? Maybe we can discuss your ICP for a bit. So your ICP worked well on the warm-up, but it didn't work for the scans, and you moved on, or you tried more and it's still
I've
didn't
moved
work?
on, but now
okay.
I'm like trying to go back because now I've like done as much of the GT SAM as I can, but it's like you just said, it won't.
Yeah, it doesn't change
It's
much.
not going to be anything.
And are you done with the mapping and
The texture, yeah.
the texture? Okay, you worked on the report as well.
I'm in the process of that.
Okay, yeah. Yeah, I mean, I'd say do everything else, and then if you have any extra time, go back to it. Yeah, I looked at the code you shared. I didn't see anything obviously wrong.
Okay.
So I don't have good suggestions. Yeah, my suggestion was try to visualize like fine grain. Like take 2 LiDAR scans and plot them and see what's going on.
Every iteration I've been printing out like the distances that nearest neighbor spits out for once the ICP converges. And when I did the warm-up, it was always really small. And I mean, it makes sense because the results are really bad from the scan matching, but sometimes those distances between the neighbors are very large.
Very large.
And I'm wondering if that means it's an issue with the ICP somehow, or if it's just because of what I'm feeding into.
I think it's very likely what you're feeding in, like
That's
your
what I think.
initialization might be wrong, like the pulse, because I know your pulse comes from the IMU and the odometry, and this looks right when you plot it, but maybe if you're doing something wrong with the frames, that might actually send it somewhere very far.
Okay.
So that's why I'm thinking plot, like pick 2 consecutive steps and plot what the scan is at time t, what is it at time t plus 1, and if you transform it according to the motion model, the one from time t should actually be quite close to the one at time t plus 1, and then you're just asking ICP, okay, these are mostly aligned, just snap them together. But if after this transformation your point cloud is here, you're already giving ICP some input that it doesn't make sense. So I would suggest plotting, make sure.
So, in the final stage of the project, the only role that the original motion model plays is just to initialize ICP.
Yes, yeah. In the way we're doing things, we essentially okay, the ideal implementation, I guess, is the motion model initializes ICP and ICP initializes GTSUM, and then GTSUM does the overall optimization. But in our project, like I said, you can get good results, maybe even just with the motion model and the mapping. That's it. You don't need GTSUM at all. But in practice, yeah, GTSUM helps because over time you get better.
I asked this on Pure Algebra, I just wanted to confirm. So like, if my ICP never works, is the scan matching something I should still put in the report and show the bad results, or should
Yeah.
Okay.
I think it's good to, yeah, I mean, again, I think one big point of our projects and reports is that you're not expected to only show good results or to do everything in the project. You're expected to try things and say what worked, what did not, and why. So I think even putting bad results and giving some guesses to why maybe things are not working, or visualizing or measuring the error, I think those are great things to discuss.
Okay.
Yeah, I think of the report this way. You spend, I don't know, 3 weeks working really hard on this, and the only person who knows about this is yourself. I don't know how much you worked, and your classmates don't know. So one way of showing the world how much you worked is to write in the report what you did. Yeah. I mean, on the other hand, write things that were interesting observations. Yeah, not like everything I did. Like on Tuesday I woke up early. But yeah, I mean, another way to think about the report is, if you give this to someone outside of our class, can they understand at least what the problem is, what the approach is? Maybe can they even start approaching the same problem without having sat through the lectures and so on. So if your report is, I mean, maybe that's too high of a bar, but you're aiming to be sort of self-contained, like someone can read it and at least be on the way of implementing an approach to this problem.
So the texture mapping and the LiDAR scan are
I would
really
say probably the scan matching as well.
It's like texture mapping and
I don't know
LiDAR
what it
It
is.
doesn't work.
Yeah, I'd like check my ICP
Oh yeah,
stuff and my
Dr.
scan
Consigrate
matching.
and
I think
the
the logic looks sound, but
and the
the
texture
ICP
are
is
two
like
separate.
if I
Right,
initialize
yeah,
it,
you're
it
actually
should be
optimized.
optimized.
You can optimize.
If like